In this example for section 15.1, we want to find the potential function f of x, y, z if f, that vector field, is conservative. To test if it's conservative, we calculate the curl. And I calculate the curl by setting up a matrix. And the curl is going to be a vector, so we want to use that notation there. We set up the vector, set up the matrix, using the partial with respect to x as that component, the partial with respect to y, partial with respect to z, and we use the components y squared z to the third, 2xy z to the third, and 3xy squared z squared. And you can break this up into three smaller matrices. Now what I tend to do instead is to use that cover-up method when I evaluate this. So I want to cover up that first column and find the determinant of this smaller 2 by 2 matrix, and that's going to be your I component. We're going to take the partial derivative of this part right here. Go back a second here. We're going to take the partial derivative of this with respect to y, treating y as a variable and x and z both as constants. And that is going to be, let's do that. Partial derivative of this with respect to y is going to be 6xyz squared. 6xyz squared. Now we're going to subtract the partial derivative going in this direction. The partial derivative of this with respect to z, we're going to multiply by 3 to get 6xyz squared, and we're going to subtract that. That's your I component. Minus, that middle one is always subtracted. We're going to move that over. Let's move that over. Now we're going to cover up that middle column there and find the partial derivatives going in this direction here. We're going to find the partial going in this direction and the partial going in this direction, and we're going to subtract. So the partial of this with respect to x, treat x as a variable and y and z as constants. That partial derivative is 3y squared z squared. And going this way, take the partial derivative of this with respect to z, and that is going to be 3y squared z squared, and subtract. That's going to be your j component. Now that last component, we want to cover up the k column. So I'm going to move that over, cover up that k column, and find the determinant going in this direction. So that's going to be plus, I'm kind of running off the page here, but go plus, we're going to find the determinant of this little 2 by 2 matrix, taking first the partial derivative of this with respect to x, and that is going to be 2yz cubed, and take the partial derivative going in this direction with respect to y, which is going to be 2yz cubed. When we simplify this, we'll see that this ends up being equal to 0. Now, if the curl of a function is equal to 0, then we can say that vector field is conservative. And if it is conservative, we can find a potential function. So the first part is calculating the curl to determine if the vector field is conservative. Since the curl is 0, it is conservative. Now we're going to set this up to find the potential function. Okay, since we know this is conservative, we're going to set up 3 antiderivatives. We are going to integrate m dx and n dy and p dz. We are treating the components as m, n, and p. The potential function is going to be a combination of those three antiderivatives. So when we integrate this m, y squared z cubed with respect to x dx, we're treating x as a variable and y and z as constants. So this antiderivative is going to be this constant times x, or xy squared z cubed, plus we could have constants, but in this case our constants can be either could be either y's or z's. So we can add a function of constants with respect to x, so it could have other y's and z's in it. So I'm using g of yz instead of a regular plus c as you would do in basic integration. Let's integrate n dy, 2xyz cubed with respect to y. We're treating y as a variable and x and z both as constants. We're going to add one to the power here of y to get y squared divided by 2. And that, when we integrate, is going to be xy squared z cubed plus, we could have constants here, but those constants could include x's and z's. So we can add a function of constants h of x comma z. Now our antiderivative of p dz would be the antiderivative of 3xy squared z squared dz. Treating z as a variable and x and y as constants, you add 1 to the power of z to get z to the third and divide by that new power 3. That antiderivative ends up being xy squared z to the third, plus we could have constants here, and those constants, since we've used g and h, I don't want to use I, j, and k because we use those as our unit vectors. Let's use the cursive L as our constant function of x's and y. So it could have constants or it could have x's and y's in it. Our potential function is what these all have in common here. They do all have in common this xy squared z cubed. So that is going to be part of our potential function. And here we could have constants, but we don't see them appearing anywhere else, any constants that include x, y, or z. So it's going to be just a simple constant c. This is our potential function. This is the potential function of our vector field. And what that means, f of x, y, z. Okay. And what that means is that if you can always check your work here. The gradient of this potential function is going to equal that vector field f of x, y, z. And recall how to find the gradient. You take this function, take the partial with respect to x and y and z, and you would get these three components.